Good morning. Great to see you. I'm very happy to introduce our first speaker today, Assaf Naor. And maybe the best way for me to introduce Assaf is by a personal story. So several years ago, I came across a paper from Fox 2015. It was about approximate modularity. And the question was some approximation bound, to place some approximation bound on two different notions of approximate modularity. And that Fox 2015 paper made a very big step by showing a logarithmic upper bound. And then I worked with Uri Feige and Inbal Talgam Cohen, and we tried to show a matching lower bound of O log M. We worked for several months. And then Uri met Assaf, and Assaf pointed us to a paper from the 80s of Calton and Roberts showing a constant upper bound. So that's the story about Assaf. And it's nice, right? I mean, in the 80s, a constant upper bound, 2015, a Fox paper with a logarithmic upper bound. So thank you, Assaf.
Thank you very much. I need
the mic, yeah.
Is this okay? Yeah? From yesterday, I noticed that those, let's say, Naor, who sit in the back, can't see the bottom of the slide or the board. So I drew a line here. Does somebody prefer the line to be higher? So I'm going to count roughly 1, 2, 3. But really, please tell me, because I couldn't see below when I sat at the back. Is this okay for everybody? And then let's draw a line here. So where shouldn't I draw below? Is this okay?
No, much higher.
Well, wait. It's not for you. Naor. Oh, you cannot see. But okay. Yeah. So the board was over there when I started, and for camera reasons, they moved it over here. So everybody on this side, do I have at least this much? No? Okay, I just won't use the board. Okay. What? Okay. Okay. So this is actually the first time I'm speaking on an iPad while standing and not sitting on my table. And I've been taught that I can do it while walking around. I'll try, but this I can't. It might be okay. There might be some funny things happening which are not on purpose. So I call this talk reverse isoperimetry, and it is. I'll show some sort of melange, some mix of results which I've been very interested in the previous few years. There is going to be. All of them are connected to each other, some very loosely by analogy, but actually most of them are connected in terms of what's going on in the proofs. And you will not see that as it goes. I will show one. I hope to show one proof. And I definitely chose this for Muli and Do after talking with you because I really think there should be many more applications of these things. So I'm going to really focus on things which I just it's kind of I feel like we need you, okay, to just to see what more this could be used for. But let me start. Let me erase this. Okay, so the isoperimetric quotient in the beginning, isoper. Of some subset, let's say omega in Rn, all subsets are very nice, compact and not non-empty interior is the obvious thing. It's IQ of omega is, so you look at its surface area and you normalize it to be scale invariant. Did I break my rule of the line? I guess not. Okay, so that is the isoperimetric quotient. And then the isoperimetric theorem is the same as saying that for every omega, IQ of omega is at least root n. You can write, whenever I write greater or equal with twiddle, I really mean the hidden constant is just a number. It's a universal constant. The isoperimetric theorem says more. It says that, that this is at least the isoperimetric quotient of the Euclidean ball, which is of, just compute, is of order root n, but in anything that I will discuss, caring about constants is a luxury. So we are there, it's much better to understand asymptotics. Okay, so this is this is what the isoperimetric theorem says. And by reverse isoperimetry, this is really kind of a silly name. It's when is questions about when can we reverse this inequality. So of course that's completely silly because you can never reverse this inequality unless you have some assumptions. And your set can be a union of many, many small balls, for example, and can have as large a volume one and as large a boundary as you want. So there's no point to discuss reversing the isoperimetric theorem unless you're asking for reversing it within a certain class of sets, okay, with some restrictions. So I guess the famous theorem is, that you can say started this is Ball's reverse isoperimetric theorem. It's from 1991. So first of all, so Ball cares about, we have to restrict the class of sets and we don't want unions of balls. So a natural assumption, which actually will be going around, will be throughout this, is that the set is going to be convex. So K in Rn is convex. And I'll also assume a centrally symmetric. Okay, so let's say it's centrally around the origin. If x is in K minus x is in K, this is just because later I'm going to apply this to norms. Essentially, all the things I'm going to say, don't assume this, but I just don't want to forget to say it when I need to. So from now on, all sets are centrally symmetric.
I'm not sure everybody knows that ball is also a person.
Well, if not, it's even more interesting, I think. Okay. Okay. And so what he proved was, and it's similar to Shachar's talk yesterday when he discussed the log-rank conjecture. So when you restrict to a convex body, you still cannot reverse the isoperimetric theorem. You can take a very, very, very long and narrow rectangle in the plane. You can make it have volume one and as big perimeter as you want. So we're still at the silly stage where it's a stupid question to ask: can we reverse the isoperimetric theorem, unless you allow a change of basis. The reason the rectangle is very long is a problem is because we're looking at the wrong coordinates. We chose the standard coordinate system, but if we chose the long edges to be a unit vector, then all of a sudden there will be a way to reverse the isoperimetric theorem. And that's exactly what Ball proved. So for every K, which is convex and centrally symmetric, you can find a change of basis, a matrix S, let's say with determinant 1, so I won't change the volume, such that the IQ of S of K is less than N. Okay, so, and actually what he got, it's less than the IQ of the cube, which is 2N. But again, I'm ignoring constants because they're just irrelevant. So for every centrally symmetric convex body, you might be looking at it in the wrong coordinates and it has a huge perimeter, but by choosing the right set of coordinates, you can bound it from above. And this is sharp. But this is the kind of thing that for people like Gidon and you are used to, this is an easy exercise, but it's actually a nice little exercise for students to prove that the cube cannot be improved. You cannot go below, and there's no better change of basis. So you have to think something about it a little bit. It's an exercise. But this is sharp. So the lower bound for everybody is root n, and the upper bound is n, and this is where we stand. And neither of these bounds can be improved. Okay? The cube. Well, I wrote order of n. I don't understand. You care about the constant. Then I think it's only the cube. Yes, but actually I'm being recorded. And I need to read the page. I don't remember. I would be surprised if not. But of course you can rotate the cube. So I guess rotations of the cube. But again, constants are eventually the field I'm going to talk to will care about constants, but that's going to be in many years. So it's really at this moment a luxury. So this is an extremely famous and useful theorem. There are a few papers in which I just use it as a black box. I needed this theorem, but many of you know this theorem without even this paper, without even maybe being aware of this theorem, because this is the paper in which he introduced a geometric version of the Bruscamp-Lieb inequality, and which is later, which he used to prove this is a non-trivial fact, and that this has been used left and right in many areas, and this is a highly influential paper. I think probably his most cited one. Okay, so that's the end of the story. In the class of convex bodies, with this thing about choosing the basis, we can always have a root n, that's an isoperimetric theorem, and the upper bound is n. I'm going to start with two themes, and which will seem unrelated, and then what I'll do is I'll explain what they're good for and prove one of them. So the first theme is really a conjecture, which I came up with. It's a long story why, but it's a new conjecture. Which I call it, which is maybe I think December of last year, so really a year ago, and I call it isomorphic reverse isoperimetry. And it says the following, so in the same setting, for every k in our n, and again, it's centrally symmetric convex, okay, there is this change of basis, which is always an issue that you have to deal with. I'll say a few words about this in a second. And a centrally symmetric convex body L inside K such that firstly L is a constant approximation of L is inside S of K, sorry, after I change the basis. So S of K is inside some C. L, C is a universal constant. And two, the isoperimetric quotient of L is the smallest it can be. Okay, so I'm suggesting that if we add a degree of freedom, which is approximate the body up to a constant, then every body is a ball. Every convex body. Didn't I write SLN? It's a change of basis. It's a change of basis. The same as in a Ball's extension theorem. So it's true for the cube. So you can look at again, I'm not gonna, it's true for, if you want the proof for all the LP balls, the paper is online from December 2029. It's on my webpage on the archive. It's true for the cube. There are weaker versions of this with I'll say in a second what they are. All kinds of weakening which are good enough for the applications I'm going to show up to logarithms, etc. But that just put the question up here. I think it's a great question to think about. If there's a counterexample, I'll be happy to see it. There are weaker versions of this question that are good for applications, and I'll get to them. But I think as a clean geometric question that I think we could explain to any ancient Greek, this is a way to reverse the isoperimetric theorem. So if you want, in the language of normed spaces, it says every n-dimensional normed space is at distance big O of 1 from a normed space for which the unit ball has isoperimetric quotient, the same as a Euclidean ball. I don't see who. Yeah, so what you do is you have to, okay, so you write a certain Orlich function. You write a certain, maybe I'll show the proof in the end, okay? It's a concrete body, right? What you can do is you can look at the eigenvalues of the Laplacian, and which give you a convex surface inside the cube, and you have to check that that there is one of them, one of the level surfaces of these eigenfunctions is actually an approximation of the cube, and that's a computation. So you have there actually, I have multiple proofs of this, and I'll maybe, if you're interested, then I'm happy to talk a whole hour on this. There are multiple proofs of this, but maybe let me get to that later. If after I show you the theorems, people prefer to see the proof of the cube, then I'll change my plans and I'll show the proof of the cube. Okay? Yes. Log n what? No, it will not be good. So it will not give root n. So the LP ball, its isoperimetric quotient grows like root n times root of p. So the question was, can I repeat the questions? All of them I have to remember all the questions, or can I start from now? Okay, from now on. Okay. So there are all kinds of weaker versions of this. So for certain applications, it's enough not. So you see here, S of k is a constant approximation of L. For certain applications, it's enough to say that to replace this. There is a weak for the volume of L is what it should. The nth root is at least the volume of K. Okay, so there are all kinds of ways to relax this. You don't want the body to be in exactly a constant approximation, but just in terms of the nth root of the volume. So I'll show applications, and these are all good questions. I think the original question has to be answered, but there are all kinds of variants left and right that you can ask. Okay, and there's a lot to do here. And if you want all kinds of classes of spaces for which we know this up to logarithms or know this exactly, you can look at the paper. This is it's online. Okay. And okay. Now I should say that okay. So there is this issue of the what did I erase this? Okay. I intended. Okay, I didn't want to erase it, but it's. I don't see who's talking, but I can add. So the question was, is centrally symmetric essential in this conjecture? I don't know. I'm going to show later an application about clustering of high-dimensional norms, rounding in high-dimensional norms, all kinds of questions that are closer to computer science. There, I'm applying this to the unit ball of a norm. So I have central symmetry for free, and I simply didn't think about the general case, but it's a perfectly legitimate question. Maybe yes, maybe no. I don't want to give an answer about something I never thought about. Okay. As a question, Dvoretzky's theorem appears in guts of proofs later if I ever get to them. But as a question, I don't see any connection. Okay, I want to say something about this change of basis that was already in Ball's extension theorem. Ball's reverse isoperimetric theorem. So there is a class of bodies which is, when I get to the open questions, which are 100-year-old, really, really old questions, these are the questions that I'm going to get to are about n-dimensional norms, which they're going to be open even for the Euclidean norm on Rn. So you don't need to. fascinating to study this for a subclass of norms, even for L2 or etc. Okay, not that reverse isoperimetry, that's easy. But when we get to the real question, so there is a class of bodies which I want to highlight, which is, so this is just terminology. So, so let's say a norm space, an n-dimensional norm space X is canonically positioned if there is only one scalar product. Only one, I mean up to rescaling. Up to rescaling, it's a scalar product up to rescaling that is invariant under the isometry group. What do they call it? Body X. Okay, so every convex body has it's a metric space. It has the class, the group of all self-isometries, one-to-one, onto mappings that preserve the norm. Isometry group, I mean, I want them to also preserve the origin, and that's by the Ulam-Mazur theorem that it forces them to be linear. So it's all the linear transformations which preserve the norm. That's a group. For the vast majority of norms, this is a trivial group. There are no isometries, but for all the norms that we will care about in this talk, this is so rich that there is only one dot product on Rn. Of course, you can multiply it by 10 or something, up to which is invariant under the group. This is equivalent to saying that this group of matrices acts irreducibly on Rn. Okay, so this is just the Schur lemma. So that is what I mean whenever I say canonically positioned. In the local theory of Banach spaces, this issue of applying first a linear transformation, finding the correct basis is what's called finding a position of the norm. This is just terminology. And so canonically positions mean that there is a canonical position. Okay, there is only one way to say, there's only one meaningful way to discuss a scalar product on the space. And then in all of these theorems, you can erase the S. And I'm going to later erase the S. So when something is canonically positioned in ball, then you don't need the S. This is already true for the original body. Okay, and in the conjecture, you would say, just don't take the S. There is already, like in the cube, there's already inside the cube some bubble which swallows the cube if you multiply it by a constant that has small isoperimetric quotient. So later I'm going to discuss only these norms, and there I won't have to discuss the S. And if you want to see the general case, it's all the analogous statements of what I'm going to say, they're all in the paper. It's not, I'm not ignoring them, but I really want to focus on these classes because the questions that I'm going to ask are going to be open even for L2 and LP and etc. Okay, good. So this is a question, and I want to spend time showing what it's good for, but I'm going to just want to, before I do it, I want to say another example of something that belongs under the reverse isoperimetry rubric, which is something that Oded and I are going to post next week, probably. It's not good to make promises because we have kids, right? And flights can be delayed. But modulo delayed flights and kids getting sick, it's going to be online next week. So this is I want to reverse isoperimetric theorem in a class of convex bodies called integer parallelotopes. So K is called an integer parallelotope if it translates by z to the n Taylor n. So I mean, if you add z to the n to k, you get all of Rn, and k x plus k intersected y plus k. has empty interior. Has empty interior.
What is XN1?
I can't write so fast. I really plan to write for every distinct xy integer vectors. So you shift it by integer. What you expect? I mean, look at the floor. Okay. So okay, any integer parallelotop massive volume 1. This is a little exercise that you can give students. And so the theorem, which I do hope to show the proof of, yeah, okay, we'll see. By Oded and I, 2022 plus epsilon, and I really mean epsilon squared, is that there exists. Why is it not going up anymore? I ran out of. Is there okay? There is an integer parallelotop K such that the IQ of K is less than n to the 1/2 plus little o 1. And I said the volume is 1, so this is just the surface area of K. Okay? So it's an honest convex body that tiles are n by translates by integers, and it has up to little o terms a small surface area like a sphere, and so this is really a convex. So if you draw this convex body and then you multiply it by 2, then the original convex body literally is like a puzzle, builds up the other convex body by translates by z to the n. And probably many of you, of course, know, but so this is a complement. I think everybody I talked to, the minute they heard this theorem of Kindler, O'Donnell, Rowan, and Wigder's 208. So it proved the same thing. There exists omega just compact, definitely not convex, with the same properties. So as I said, z to the n plus omega is Rn. The same thing, x plus omega, y plus omega. Oops. Has empty interior. Let's say measure 0. And the IQ of omega, which is, in this case, is root n. So there is no little o term in this. So now this set looks like some sort of amoeba. It's definitely not convex. Those of you who know, there is some random shifting argument, which is, again, in the guts of the proof, very common from the theorem, shares a common theme with the theorems I'm going to show you. So the fact that you can tile by a puzzle piece, the way I said, but that's not a convex body. That was known since 2008. There is a lot of work on this. This is, again, I am related to proving impossibility theorems for strong versions of parallel repetition. And there are multiple proofs, and Dor has a very nice study this, what happened when you want the body to be symmetric, et cetera, et cetera. So I definitely remember the conference when they presented this, and I think everybody in the room asked, what about a convex set? And I can tell you that, so it's kind of unclear to me if the fact that there is an amoeba that tiles are n by integers should imply that there is also a convex body. And the reason is that the minute you impose the convex body tiles are n by translations, then all of a sudden you have a lot of algebraic constraints. So Minkowski's first theorem, I'll say it quickly, because then it's related to a question I want to ask. It's 1897, I checked yesterday. says that, so if K is convex and tiles are N by translations, that can be any lattice, doesn't have to be Z to the N, then firstly, K is centrally symmetric. Symmetric means centrally symmetric. 2, every face of K is symmetric. 3, for each face of dimension n minus 2, every n minus, I should have said every n minus 1 dimensional face of K is centrally symmetric. Now I go one below, every face of dimension n minus 2, so you have some polytope. K is symmetric polytope, I should have said that. I never said it. It has to be a polytope, that's kind of obvious, but you have to prove it. It has to be symmetric, every n minus 1 dimensional face of it is symmetric. If you go to an n minus 2 dimensional face of it, then there is the orthogonal complement of the space is a 2-dimensional plane, and you can look at the shadow of your polytope on that plane. You can project it orthogonally onto the orthogonal complement of the n minus 2-dimensional face. That's a 2-dimensional plane. So for each, the projection of K onto its orthogonal complement is either a parallelogram or a centrally symmetric, it has to be symmetric hexagon. Okay, so these are constraints that when you project that any 2-dimensional shadow, when you choose the dimension to be orthogonal to a face, what you see is a hexagon or a parallelogram. And then Venkov in 59 proved this is if and only if. It's a nice fact. This is if and only if. So that's the only. That is the same thing as being able to tile Rn. And Minkowski's second theorem again, the same paper, is that if K tiles are N, tiles are N by translations, then, and it's convex, I mean, in the world of convex, okay? Then, there are only finitely many combinatorial types. That K can have. Okay, combinatorial, it means of course there are infinitely many possible shapes that tile are N, but in terms of their combinatorics, how many faces of every dimension, there are only finitely many. Okay, unlike amoebas or compact sets where there is a huge amount of options. So I'm going to say something very vague, but this is something that I've been trying since this 208 work, the proof with Oded is, it's not even the connected component of their approach. There is no similarity because we're producing one of these very restricted polytopes. But I would be very curious, and I think it would be very interesting to see if there's any way to transform an amoeba, like in this old paper about form, into a convex shape. You were going to have to fall into these finitely many combinatorial types and these constraints. So it's not going to be, it has to be something that starts with something compact that looks crazy and produces a polytope with a lot of constraints. So if there is a way to pass from one to the other, I think that would be interesting. And I'm vague on purpose because I don't know because both facts are true. But I would somehow want to correct something and magically fall into this constrained set. So we just simply go on a different route. Okay, and I do hope to show the proof. If I'll run out of time, I'll show it to whoever is interested. Okay, again, the other open question for this community is what is this good for? Okay, so for the applications for impossibility results in parallel repetition, we couldn't care less if the body is convex or not. Okay, now there is a convex one. Is it good for anything? I have no clue. Okay, so I think it's available to us. It's a standard tile like the floor we're on. What is it good for? Okay, so my plan is to now pass to applications of the isomorphic reverse isoperimetry. Just, yeah.
About the question, if you need to relax the perfect timing condition, ask you to tie like 1 figure of one of the space for any nice measure.
The answer is yes, and that is really one of the connections with his isomorphic reverse isoperimetry, because you can start with the usual cube, take the set inside, which is a constant approximation of the cube, and then so when you start tiling it as though it's the cube, it misses only a little part of the set. So things like that, yeah, so it's true. And you can also relax tiling maybe by saying you bound the overlap, or maybe the overlap of a typical point. There are many ways to relax tiling. All of these questions are legitimate, and then equally legitimate is what are they good for, to ask. Okay. So I mean, in the case of these convex bodies, I have plans, but I need to think about them. There are many things in analysis where you look at the dyadic decomposition over n, and you Calderon-Zygmunt decompositions. I mean, I have plans to. The surface area appears in these things a lot, so this could come in. Yeah, but anyway, there's definitely this is for the future. Okay. Yeah.
The symmetry group is, you have only the canonical.
Good question. I do not know. Are they canonically positioned? I don't know. Probably not, right? Or did? Canonically positioned. The position is canonical. This is I think. I do not know. We never thought about it, but I have no idea. If the answer is yes, then the last question that we wrote in our paper has a solution. So the answer is. Yeah, but anyway, we have to think about it for 1 minute, because there is an open question in the paper that would solve. You know what I'm talking about, but I don't know. Okay. Okay. Yes.
You know what is the number of faces of the body be?
I have no idea. I'm sure there should be. I'm sure it should be. Well, we didn't get up to the little of one thing. Should be exponential, but again, I didn't think about it. I'm sure there should be. Right. That is doable. Let me think about this offline. Okay. Okay. So I completely lost track of time. When did I start, and how much time do I have? Just so. Okay, so I'll aim for 1 hour, and I'll stop there. And if you guys force me to talk, then I will be happy to oblige. Okay, to continue. Okay, so what I'm going to do now is I'm going to go back to the original question, the reverse, which is mostly a conjecture. It's proved up to logarithms and all kinds of, or for special classes of bodies. And I want to show you how I got there and what it relates to. And it relates to things which are very much studied in computer science already. But along the way, I think that there are many more things that I think could be done. So this relates to 2 questions. One of them is about extensions of Lipschitz functions, and this is where I came from. And the other one is clustering of high-dimensional norms. And I'll start with Lipschitz extension, because that's older. Lipschitz extension. Again, I'm going to show really 1% of what's the topics and questions that can be asked. I'm going to show only things that are really directly relevant to the reverse isoperimetry. So there is a bi-Lipschitz invariant that you can associate to every metric space. So you start with a metric space. Let's say MD is a metric space. And we say that EM it's a number. I'll call it this is the Lipschitz extension modulus. Of M. So, and then you're gonna see tons of quantifiers. It's a very strong parameter. So it's the smallest L, the infim over L, such that L is not a convex body anymore, it's a number. So, and now I'm gonna say for every subset A of M, okay, so take any subset. For every a Banach space Z, okay, and I'm saying Banach space just because this is classically what's studied, but the target, this is the target of the Lipschitz function. Everything I'm going to say happens also, it works if the target space is, let's say, manifold with certain curvature bounds. So there is a lot known which I'm not saying. So for every subset of A of M, for every Banach space Z, for every function f from A to Z, which is one Lipschitz, everybody here knows what Lipschitz is? The image between fx and fy in Z is at most the distance in M between x and y for any 2 points x and y. So whenever this happens, take any subset, any target space, any one Lipschitz function on the subset, there exists a function f which is defined in everything, defined in M, which is, that is L Lipschitz. L was the thing I'm trying to minimize. And extends F. Okay, so this is, so saying that the Lipschitz extension constant of this room is less than 100 means that that's this room with Euclidean geometry is that if I look at the subset, which is the hairs of all of you, and I take a Lipschitz function going into a crazy Banach space, but it's one Lipschitz, but it's defined only on the hairs on the top of all of your heads and beards, okay, then I can extend it to a 100 Lipschitz function, which is defined in the entire room, okay, also on my belly button, okay? So that is so you understand, so saying that this number is small, that's what it means. Is that clear? Okay. So this is kind of, once you have a bound, this is, I think every other paper that I write, but this is really definitely every day, maybe every day in the archive, there's a paper which uses the Lipschitz extension theorem. It's completely common that in situations, maybe all of you already encountered them, that you have a function which is defined in some subset and some discrete subset. You want to analyze it, you want to convolve it with something to smooth it out, you want to maybe differentiate it, you want to compute its Fourier transform. All of this doesn't make sense unless the function is defined in all of Rn. If, let's say if any is Rn. So extending a function in order to just analyze it is something which is done left and right. And there are also deeper applications to computer science. And I recommend looking at the paper of Kostya and Yuri Makarichev, where they show that extension problems are equivalent to sparsification problems, just really if and only if. Okay, but is the question clear? This is, if somebody provides you a bound on E of M, this is a number which is a by Lipschitz invariant, and it's a good number to know. In a one thing that I want to emphasize, and this is going to be in one slide or in 1 minute, is this is a by Lipschitz invariant of the space itself. Okay, so you give me some graph group Rn with some norm, etc. So, but I formulated it using a target space and a Lipschitz function. Okay, but this is something about the intrinsic geometry of the space X. So there must be a way to rewrite it in terms of just looking at the geometry of the space and not mentioning any external objects. And that you will see is a very interesting rounding problem, which I will get to later. So I will formulate. But this has to be written with not the way I wrote it. The way I wrote it is the way people think about it and use it, but there is a dual way of writing this, which tells something about the geometry of the room. How does this room interact with the hairs on your heads? Okay, so, and we'll get to that, I promise that we'll get to that. Okay, so So again, lots of literature. Let me just say a big paper, famous paper from the 80s of Johnson, Lindenstrauss, and Shechtman from 87. They proved that if X is an n-dimensional norm, then E of X is at most 100 times n. Okay, so for n-dimensional spaces, no matter how crazy some fractal Julia set, you have a function defined, and no matter how crazy the Banach space that it's going into, you can always extend a 1 Lipschitz function to an n Lipschitz function. And just to show this is this is a famous theorem. I think by now there are 4 different proofs of it. The great open question, central open question is, can this be improved to little O of n? We have more proofs of this, but they always give n so far. So and I simply don't know, question mark. Okay, so that's a very nice question. You give me an n. And generally, compute E of X for any. By compute, I mean up to universal constants or up to little order terms. For any n-dimensional X. This is norms, let's say up to lower order terms. So this is even open for Hilbert space. Just this room with the usual Euclidean geometry. We don't know the asymptotics. I'll get to this in a second. Let me just tell you what the enemy is. So what I'm interested in here. So there is here. So in the same paper, that's a line. I prove that if X is an n-dimensional norm space, and then E of X is at least n to the C, where C is a universal constant. Okay, so the game is, so the Johnson-Lindenstrauss-Shechtman theorem says that it's at most n, at least n to the C. So when I say compute this parameter for any space, L2, spaces of matrices, etc., I care about what is the exponent. The game is the exponent. There may be lower order terms, which eventually we'll care about, but the game is what is the exponent of the dimension in this story, okay? The fact that this goes to infinity for any normed space was open since the Johnson-Lindenstrauss paper, since the early 80s. Many people asked it. And the fact that it goes to infinity at some rate, this is something that I did in my dissertation, so over 20 years ago. And that's where Dvoretsky theorem comes in. So it's enough to show it for Hilbert space, and then you get, but that gave little O of n to any constant. So there is something more here. I recommend seeing this proof because there is a lot of fundamental questions in Banach spaces which it raises, which I think should be solved. But I just want to say that there is a different proof of this, completely different, using this dual approach, which I now will explain, of Braverman and myself. It's again 22 plus epsilon, in the sense that it's written but has to be posted, which gives a different proof. Different proof, which gives more because of its perspective, and I'll get to that later. Okay, but in particular, it gives a better constant C, but I don't. That's not the point. It's genuinely a different reason. Okay, so now the game is. So I want to say. So when I say so, great open question for everybody here. I don't understand why it's not moving. So open, and in a second we'll see what the dual of it means. Is a compute E of L to n, Rn with a usual Euclidean metric up to lower order factors. So nothing crazy. A question about Euclidean space. At the moment, it feels like a question about Euclidean space and a target Banach space, right? So it's not really a question about Euclidean space. So now let me tell you what the dual is of this problem. And then you'll see that it's a clean question about Euclidean geometry, which we do not know how to answer. So currently, we do not know what the exponent of n is. for just Rn with a Euclidean norm. Again, I don't see who's asking. Do I have a guess? I do. It changes daily, but and I don't think you should care about my guesses, but I appreciate it. Okay, I'll tell you today's guess today, and we can talk again tomorrow. Okay. I have a hope. I can tell you, I have a hope, but not. But so that's equivalent to a guess that won't happen, I guess. But okay, okay, we'll get to that. So I wanted the dual of this Lipschitz extension problem is really a rounding question, which it's equivalent to this. So this extension question has been studied forever in mathematics, also in computer science. The dual is equivalent. So everybody in the area studied the rounding question that I'm going to formulate without knowing it, okay, or with knowing it, but it's just equivalent to the original question. Nevertheless, I have not seen applications of this in computer science, and I want to show you a twist to Bourgain, which really raises interesting questions in computer science, I think. So the dual is called Wasserstein rounding. When I talked with Dor before this, he told me, please don't say the word Wasserstein because it scares people. So I'm sorry I revealed that. Maybe I'm saying something personal about you. So yeah, I'm sorry if you get scared. It scares me too. Okay, so here's a rounding scheme. So remember, I'm in the setting. I have a metric space, MD, symmetric space, and A is a subset of M. And now I really want to discuss. Now I'm going to discuss about property of the hairs on your head or the integer grid in this room. I'm not going to mention Banach spaces, and I'm not going to mention Lipschitz functions. So the goal. So for every x in M, every point in the ambient space chooses, or you chooses a probability measure, mu x, supported on the subset A. Okay, so every point outside somehow decides how to distribute itself over the hairs on your head. Okay. And you want two things. Firstly, it's a rounding question. So if x happens to be in the set A, then mu x is the delta is the delta mass at itself. It's already happy. Okay. And the second is, what did I do? Delta of x. Okay. And for every 2 points x, y in the space, you look what is the mu x minus mu y in Wasserstein 1. I'll explain to this one. That's less than L times the distance from x to y. So the Wasserstein 1 distance is just the earth mover distance, the transportation cost distance. These measures are supported on your hairs. Okay, so every point decides on its own to choose a random hair. But you want 2 points if they're very close to each other, that there is going to be a way to match these, to find the coupling of these two measures, such that the expected distance between a point and its match point is small. And depend how small, L is the same L in the L is just the smallest L, the infimum over the smallest L is just this E of M. E infimum over L and supremum over all subsets, right? Is this E of M. For every subset, you can ask the question. Okay, so this is a very, very, very clean question, right? You just and the proof that this works is one direction is the minute you have these functions, the minute you have these measures, and remember you had the function from A to a Banach space, then just define f of x to be, just look at f of A, integrate. This is obvious. Integrate on A. It's the original function is defined. Just check that it works. Converse is equally easy. those of you who know Kantorovich duality know that that Wasserstein 1 is the dual of the space of Lipschitz functions. None of this is surprising. Everybody knew this forever. Okay, this is the same thing. With one caveat, which is I lied to you. There's something special about this extension formula. And the truth is actually more complicated, but we know how to handle it as well. Observe that because mu x is a probability measure, u sub x is a probability measure, this f of x belongs to the convex hull of f of a, the image, maybe the closure. Okay? Because it's an average. In the Lipschitz extension problem, I never restricted the extended function to take values in the convex hull. Any extension theorem, and many of them are, those of you who know Kirschbaum's theorem or Ball's extension theorem, that work by like a separation theorem. If there is no extension, you can find the hyperplane and you reason, will immediately produce extensions into the convex hull, but that's not always true. Okay? And actually you can compute, you can give examples of functions which are extendable to the superspace, but you simply cannot extend them into the convex hull. There are examples of this type. So in order to make, so this is a version which, I wrote here, this is what I call econv. So econv of M is the smallest L such that every one Lipschitz function from a subset A to a Banach space can be extended to an L Lipschitz function, capital F, but you not going into Z, but going into the convex hull of the image. Okay, this is for those of you know this happens a lot, but not always. Okay, so in general, what you have to do is you have to take mu of x not to be a probability measure. You have to write it as mu x plus minus mu x minus, a signed measure. You want them to have the same total mass. Okay, so the total mass of mu x is 0. So this allows you, this means that when you integrate it the way I did, you are in the span, but not in the convex hull. And there are some integrability. They have to have finite first moments. And then what you do is, and again, mu x is the delta at x if x is in A. And then what you do in general, ux, if you take xy in the superspace, then you look at mu x minus mu y, and you write it. I mean, this is some measure which is total mass 0. So you can write it as mu x minus mu y plus minus mu x minus mu y minus, and then the condition is that the Wasserstein 1 distance between mu x minus mu y plus and mu x minus mu y minus is here, is less than L times dxy. It's the same thing, but it's more complicated because well, that's the truth. And this is the real question. Okay, everything I'm going to say works in both. We know how to understand both of them. I just want to say that this is something that I'm still surprised by it. This is so in this upcoming paper with Braverman. So I don't know about others, but I definitely in many places over the past 20 years conjectured in writing that this what I'm going to write now is not true. Is that E of M is finite if and only if E conv. This follows from like a series of equivalent formulations where we study the dual. So it's actually the same thing, except and it's not quantitatively. So we can bound one by some function of the other, but they're not linear functions. So, but actually it is, if you can extend, this is very surprising because there's, 5 minutes, So there are specific functions that I know cannot be extended to the convex hull, but when you add a quantifier for every function, then actually these are the same notions qualitatively. So this is something that even when I write it, I didn't expect this to be true, but it is true. Okay. So and maybe I should just. You can wonder. Another thing that I've been wondering about for a long time. We discussed it with Gideon, but definitely. So you can look there. You can ask about this rounding question. Let's go back to classical Diophantine rounding. You want to round Euclidean space in this sense to the integers. So what is the best way to round Rn with Euclidean norm to the z to the n? So every point outside the integers has to choose a distribution over integer points. We do this all the time, but I want this to the guarantee is to be in the sense of matching this expected distance in the transportation cost. So again, in this forthcoming paper, by studying the dual, we can prove that for a is z to the n, x is L to n, the answer is up to universal constant, n to the 1 over 6. So if you want to take a point in the continuous space and round it into an integer in such a way that 2 points are close, that the measures are close and in the sense of coupling an average, you can do it with n to the 1 over 6 and you cannot do better. And there are all kinds of things that you can get from the dual. And again, this will be on line today plus epsilon. Maybe not epsilon squared, epsilon. Okay, so I have 3 minutes. Okay, so I want to say, in the end, I'll say something about the clustering, but I want to say something which is speculative from the philosophy of rounding, which I want to discuss Bourgain's variant. Yes, but Wasserstein is simply the original question. Okay, I think this is interesting also in terms of like the Diophantine approximation. You take a point and associate a random integer. How close can you be when you just want the points to be near each other? There's something which I like very much, and I've seen decisive applications of it in mathematics and none in computer science. So this is Bourgain's approximate, how do you call it? Almost extension theorem. I even forgot how he called it. He called it almost. And I don't know how to erase. Bourgain's almost extension theorem. So this is from 1987. So remember I told you that this E of M for every space is at least n to some constant. It goes to infinity. So when you have a 1 Lipschitz function defined in a subset, you can never hope to extend it to a function which is 10 Lipschitz. Okay? But there was a concrete application called Bourgain's discretization theorem, a new proof of Rebbe's theorem, a major application, where getting the extended function with any Lipschitz constant going to infinity kills the application. Log, n. It simply kills the application. At least in the approach that why is this not moving? I have no idea. So the computer is programmed to make me stop speak, or that's why. I have no idea what's happening, so I can write. Huh? Oh, press and okay, got it. That's a pretty good idea, by the way, for future speakers. So Bourgain's almost, so he changed the question and he said the following. So you can do it about the entire space, the sphere. So let's say, so you take X is an n-dimensional norm space. There are variations. I'm going to say the original one, n-dim norm space. Space Z is any norm space, any Banach space. And you take N is an epsilon net in the unit sphere. Of X. Okay? And now we have a function f just from the net to Z, which is 1 Lipschitz. Okay, so you have a function which is not defined. You have your sphere. It could be the sphere of L1, so it's the epsilon net in the L1 norm in the octahedron. You have a function going into some Banach space, which can be crazy and will be crazy in many applications. And it's 1 Lipschitz just in the discrete net. Okay, so he proved. So this is Bourgain's theorem. that you can find the function f, which is defined in all of x into z, okay, such that the Lipschitz constant of f is a universal constant, let's say 10, okay, 2. You can get 1 plus epsilon versions of this now, but some universal constant. So this is decidedly impossible if you want it to be an extension. Okay, so you give up the idea that it's an extension. So for every a in the net, f of a minus f of a, this is in the norm of this target space z, is less than n epsilon. So he put the n that was in Johnson, Lindeshaus, Shechtman, the Lipschitz constant was n. Now he made the Lipschitz constant be 10. That's crucial for him. He extends it, he convolves, he looks at the Fourier transform, he differentiates. The norm, the Lipschitz constant is the norm of the derivative. It enters in many, many places in the proof. And he forfeits extension. He just says, I just want to be wherever capital F of A goes, if you're a net point, it has to be near little f. Okay? So I just want to say that this is sharp. So n is sharp. So in 2020, I proved the lower bound that you can get n to the 1 minus little of 1. But again, in this paper with Braverman that's coming, again, looking at the dual, we just got it. So n is completely needed. Omega n is needed. Okay, so if you insist of being 10 Lipschitz, but only near points in an epsilon net, the best you can do is n times epsilon. Okay? But what is the dual of this? You can go through the motions, and let's look what is the dual of this. And I'll say the dual in the sense of extensions into the convex hull rather than the sign measures. You can, in your head, it's all written in the paper, so you can. But the dual of this is again every x in Rn in x, right? It chooses mu x, which is a probability measure, on the net, on the epsilon net. Okay, we want the Wasserstein 1 distance between ux and uy to be less than dxy. In this case, it's a norm. Okay, but you give up on the fact that you extended. So what does this mean? It means that you look at ux minus the delta of x, and you want or the distance, the Wasserstein 1 distance between ux and the delta of x to be less than na for every x that happens to be in the subset. Okay, so it's the same thing. A point in the continuous ambient space rounds itself randomly to a point in the subset, but just you also allow points in the subset, not integer points if you want, to remain, you don't insist they remain themselves. You just want them to be, you allow them to also distribute themselves. And you just want that this distribution is close to the delta mass, geometrically. Not Na, and epsilon. What happened? Epsilon is the epsilon of the net. Okay? So this is completely decisive. Bourgain and also elsewhere, this is a decisive tweaking of this extension problem. It leads to a tweaking of the notion of rounding, which I have not seen used in the same level of decisiveness in computer science. Okay, so right? Sometimes what happens if we don't round to for the application he had in mind, you really, really need it. I would be happy to see an algorithmic application for that as well. So I'll stop here. I guess every talk that I ever give, I do a third of what I planned. So now I did 2/3. There's a whole, so I feel better about it. You gave me more time. I'll answer any questions. There's a whole chapter about clustering. So there is a clustering, a standard clustering paradigm that has been used a lot in algorithms. And using this reverse isoperimetry, I just can give, for every n-dimensional normed space with this canonical position, in this canonically positioned, I can give a formula for the best possible way to cluster it. So again, in reverse isoperimetry goes into that. So that's one topic that I completely didn't talk about, but I can explain. And that's actually, I don't have to speculate about applications. There's a huge body of work in computer science about that. Many of you know. And then the other thing, which I didn't talk about, is show the proof of the parallelotop result with ODED, which I'm happy to talk to anybody who wants. So I can continue, I can stop. I'm stopping unless you force me. Okay. Yeah, can I write it? I said, okay, so let's, if you have a metric space, so let's call EAM or MA, I don't remember. Matuszek is the one who invented this notation. I never remember. Yeah, Gil, everything is commutative. Yeah, so EAM is just the smallest L. I just removed the subset, the smallest L, such that for every Banach space Z, for every one Lipschitz function just is defined an A. There exists a function defined in all of the space, which is A Lipschitz, F is. And F coincides, F extends F, F coincides with little f on the set A, okay? So what we proved is using this notation that Ez to the n, L to n, I know exactly what happened. Integers, yeah, integers, is bounded above and below. Yeah, yeah, but you have, I agree, but you have to make this happen in with small probability. It's Wasserstein. So first of all, the way I formulated this is just, the way I formulate this is about extensions of Lipschitz functions. You have a function which can happen to anyone, like an applied mathematician is a function which is defined in the grid, and you want to compute its Fourier transform, right? The dual is that a point outside the integers is choosing a random integer point. Some integer points are going really, really, really far away. But there is a way to match, if x and y are close, there's a way to match these, to do a coupling of these distributions so that the expected distance matched is n to the 1 over 6, and you cannot do any better. And this is also true in the sense of these sign measures, which is much more complicated.
Do you suppose that the discrete set is the worst in this case?
Okay, so that's again, this is for, again, not all, but many of the applications of Lipschitz extension, the subset A is a net. Okay, it's really so you can define E net of M as the smallest L for extending from nets. Okay, that's a parameter that actually people really care about. Not always. Sometimes you extend from more complicated sets. Okay, but so and another theorem in the same 2022 plus epsilon paper with Braverman is that E net of L to N is n to the quarter. Okay, so Z to the n does much better than n, worse than n to the 1 over 6. So Z to the n behaves worse. It's less compatible with Euclidean geometry. But for any net, if you want to extend from a net, then you have to pay n to the 1/4, and you can pay n to the 1/4. And you can ask, I guess, this question, which is very legitimate question, which is E net, at least for a Banach space, for an n-dimensional normed space, is E net the worst? Is the net the worst? We're in a continuous space, we want to somehow round it to something, to a subset, and epsilon net feels like the worst. So I know the answer, so I can give examples of spaces which I know the answers are different. A plus, right? No, the plus doesn't come up. Okay. Yeah, I'm applying it to myself. I mean, so again, in this paper, the main, I don't know, headline result, if you want to say a headline from 2021 is that I computed the E of L infinity n, and that's up to universal constants, root n. Okay, and that's actually the only space for which we know it's E, the extension modulus. Okay, but in this paper with Braverman, we proved that E net of L infinity n behaves like in L2. So for L infinity n, the worst set is not a net. And that's a good question. For which spaces is the worst set a net? Eitan, I mean, I really would be happy if the worst set in L2 would be a net, because that would solve the question. It will give that the answer is n to the 1/4. And it will also be a nice picture, like the worst possible set is a net. But we have to be careful because it doesn't happen always. So sometimes it could be some crazy Julia set or something, and we need to understand. There's a lot of work to be done here.